So this is a quick video aiming to explain to you what a Bohr-Rutherford diagram is and how to construct one on your own. So before we get there, I want to remind you of Rutherford's nuclear model of the atom. So you may remember that he's the gentleman, the scientist who did the gold foil experiment. And through that experiment, we were able to determine that there had to be a center of positive charge within the atom. And he called that the nucleus. And now we know that that's where all the protons are. But he didn't really have any idea about where the electrons would be, and so he just sort of put them randomly, just around the nucleus. And so the job of scientists that followed him were to determine where exactly these electrons were. And so the next scientist that came along, Niels Bohr, he proposed that planetary or the solar system model of the atom, and that sort of provided an explanation about what was going on with the electrons. And so he had a few ideas, and before we get into drawing the Bohr-Rutherford diagrams, I just want to go through what those different ideas were. So he believed that the electrons would have to be able to orbit the nucleus, just like satellites orbit planet Earth, and also how planets orbit the sun. And somehow he thought that if that were the case, then the electrons, being negatively charged, wouldn't spiral into the positively charged nucleus. So the next thing that he proposed was that electrons can move from one orbit or one energy level to another, but they can't exist in between. So sort of like if you were climbing stairs, you can either be on one step or the other, but you can't be in between. So you're either on the first step or the second step. There doesn't exist any step in between that. So an electron traveling in one particular orbit would have to gain exactly the right amount of energy in order to move or jump to a higher energy level. There was no existing in between. So to create a bit of a visual for you, so let's just say that there's this electron right here in this first energy level, and we somehow shine some light energy on it, or we add some electrical energy, whatever it be, any form of energy. If there's enough energy added, then it will jump to a higher energy level. Right? So each energy level has a specific amount of energy associated to it. So for example, remember that our nucleus is positively charged, right? And so if I'm talking about an electron that's in the first energy level, as opposed to an electron in the second energy level, I know that because electrons are negatively charged, then an electron that is in the second energy level must have more energy. And the reason for that is that electrons, being negatively charged, are going to be attracted to that positive pull of the nucleus, right? Those protons. So an electron that's further away from that positive pull must have more energy because it was able to sort of escape that pull from the nucleus. So that brings us to the final two statements that Bohr said about the atom and where those electrons are. So he said that the closer an electron is to the nucleus, the lower its energy and the more stable it is. And the farther that electron is from the nucleus, the higher its energy and the less stable it is. And so think about it like, imagine it's the nucleus is kind of like a bad habit that you're trying to break, right? So let's say watching video games. And so you know that the farther away you are from those video games, the more likely that you are to want to go and play them. The less stable you're going to be, right? The more you're going to sort of feel unhappy. And the closer you get to being able to use those video games, play those video games, the more of a relief you'll have. So electrons are sort of the same way. The further away they are from the nucleus, the less stable that they are because they really want to be close to that nucleus. So electrons that are closer to the nucleus are just a little bit more stable because of that. So now we get to the drawing of the Bohr-Rutherford diagrams themselves. So it's important that you know that the first orbit, or the first energy level, that's the one that's closest to the nucleus, can hold a maximum of 2 electrons. Okay? It can hold 1 electron, but it can hold at a maximum 2. So I'm just going to draw these in here. Okay? And the next energy level or orbit after that can hold a maximum of 8. But there's a way that I want you to draw those in, and there'll be reasons for that if you continue to take science, but let's go with it. So the 8 that I would draw in, I want to draw them in all 4 corners of the world here. So 1, so 2, 3, 4. So think about that like north, south, east, and west. And then I start doubling up. So I don't want to double up the electrons until there's 1 in each of the 4 corners. And then I would go on ahead and do that same thing for the second orbit. Okay. Now you'll remember that each element, what defines an element is the number of protons that we see in the nucleus. And so because of that, when we're drawing the Bohr-Rutherford for a specific element, we need to take into account the number of protons, the number of electrons, and the number of neutrons when we're drawing out a diagram for a particular element. So let's go through an example together. So I'm going to use the example of lithium. Okay, so lithium, when I look on the periodic table, and you should have one handy, so if you don't, pause the video and make sure you go get one. But when I look at the periodic table and I look at the atomic mass of lithium, I can see that it's 7.94. And so I'm going to round that, or 6.94 rather. So I'm going to round that to 7. And when I look at the atomic number for lithium, the atomic number for lithium is 3. Right? And so by knowing that, I know a number of things about a lithium atom. I know, first of all, that the atomic number tells me the number of protons. So I can write that out right off the bat. I can write that the positive protons, I have 3 of them. And I know also that if this is a neutral atom, and we're going to assume for this case that it is a neutral atom, that the number of negatively charged electrons are also going to be 3 for this particular atom. And then you may remember that the way that we get the neutrons is a little bit less obvious. I need to take the mass number, which is the protons plus the neutrons, and subtract the atomic number. And when I do that, I get the number of neutrons. So this tells me that I have 7 minus 3, or 4 neutrons. So now I know that I have 4 neutrons. So now I can start filling this in for my diagram for lithium. So if I'm drawing a Bohr-Rutherford diagram for lithium, I'm going to place my 3 protons. This is a little messy, people, bear with me. My 3 protons in the center, because that's where the protons are found. I'm also going to try to fit this in here. It's going to go out of the edges here, but imagine that it's all in there. I'm going to put my 4 neutrons there, because that's where the neutrons are found, in that nucleus, right? But now I'm going to start to populate these orbits with electrons. So I normally would not have all of these orbits present. I just draw them in as the electrons are filling them. So let's see where we get with lithium. So with lithium, I have 3 electrons. And I always fill electrons from the first orbit outward. So in this first orbit, I'm going to put 1, 2 of my electrons, and I can't put the 3rd in there because only 2 can fit in that first orbit. So now I've used up 2 and I only have 1 left. So where is that 1 going to go? Well, it can't go in the first energy level, so I'm going to put it in the next energy level too. So really this whole outer orbit here would not need to be there at all if I were drawing the Bohr-Rutherford diagram. All right, I'm going to show you a different one, another one. And this time, I'm going to choose fluorine. So fluorine, if you look at the periodic table, you can figure out how many protons, neutrons, and electrons it has. So I'd like you to pause the video now and get that information for yourself, and then check it out after by continuing the video. So fluorine has a mass number of 19 when I round off, and it has an atomic number of 9. And so what that tells me is that I have 9 protons. And so I'm going to write that in. And assuming that this is neutral, I'm going to also have 9 electrons. And I get my number of neutrons by saying 19 minus 9, which will give me my 10 neutrons. So again, now I'm ready to go. So I've got 9 protons, 9 electrons, and 10 neutrons. My protons are going in the nucleus. Let's try to make this a little smaller. So 9. I've also got, oops, nope, those were protons. And I've got my 10 neutrons. And now I've got 9 electrons to place in my energy levels, right? So I've got my 1, 2, and then I've got 7 more to go. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9 electrons. So there I go. So again, this third orbit or third energy level really doesn't need to be there. It's just there because of the previous diagram. So normally I would just omit that completely. So hopefully you did okay and that you're ready to start the worksheet that was handed out to you for the Bohr-Rutherford diagrams. If you need any extra help, please feel free to come and see me on Monday.